Hello viewers, in today's class we are going to solve yet another problem from linear differential equation, right? So here we have to solve this linear differential equation that is dy over dx plus y cot x equal to 2 over 1 plus sin x when the conditions are given, that is y is equal to 0 whenever x is equal to pi by 4, right? So here what we will do, we'll first find out the general solution and then we'll make use of this condition or the boundary condition to find out the particular solution of this differential equation, right? So let us start. So here if we closely look at this equation, then we see that this equation is similar to the form which is dy over dx plus py is equal to q. So this is the standard form of linear differential equation of first degree and first order, right? So here if we compare both these equations, then we see that p is equal to cot x, right? And q is equal to 2 over 1 plus sin x, right? And both p and q they are functions of x, right? So we have established that this given equation is a linear differential equation of this type, that is dy over dx plus py is equal to q, where p and q are the functions of x, right? Now what we do here, we'll find out the integrating factor of this differential equation. So the integrating factor is given by e raised to integral of p, where e is the famous exponential number, right? So here we have to find the integrating factor, that is e raised to integral of p, that is p is cot x, right? And we know that integral of cot x is given by log of sin x, right? And here e raised to log sin x is simply equal to sin x. Why? Because we know the result, that is e raised to log of say some function f of x is equal to f of x, right? So here f of x is equal to sin x, so e raised to log sin x is equal to sin x, right? So therefore the integrating factor of the given differential equation is given by sin x, right? Now we have to write the general solution. The general solution of this type of linear differential equation is given by y times integrating factor equal to integral of q times integrating factor. Here we have dx, then we have the constant of integration, right? So the general solution is directly given by this expression, and now here we'll put the value of the integrating factor and q, right? So we have y times integrating factor, which is equal to sin x, and here we have q is 2 over 1 plus sin x, and here we have the integrating factor as sin x dx, and c is the constant of integration, right? So now viewers, here we have to find this integral, right? In order to obtain the general solution of this differential equation, we have to solve this integral, right? So let us call this integral by I1, and I1 is given by 2 sin x over 1 plus sin x, and here we have dx, right? So now viewers, in order to evaluate this integral I1, what we will do, we'll take 2 outside the integral sign, and we have sin x dx over 1 plus sin x, right? Now we'll add and subtract 1 in the numerator, right? So we'll write it like this: 1 plus sine x minus 1 over 1 plus sine x, right? Because we are adding and subtracting 1, so it will not going to make any difference. And now we'll separate this integral from here. So we have 2, and integral of 1 plus sine x over 1 plus sine x dx minus integral of 1 over 1 plus sine x dx, right? So now here we have these two terms get cancelled, and we have integral of dx, which is simply x, and here we have integral of 1 over 1 plus sine x dx, right? So now viewers, we can rewrite this expression as 2x minus 2 times integral of 1 over 1 plus sine x dx, right? Now in order to obtain the integral of 1 over 1 plus sine x, what we will do, we'll multiply the numerator and denominator by 1 minus sine x, right? So we have this expression, and we are multiplying the numerator and denominator by 1 minus sine x, right? So let us see what we get. So we have here 1 minus sine x, and here we have 1 plus sine x, 1 minus sine x, that is cos square x, right? Because 1 plus sine x and 1 minus sine x is 1 square minus sine square x, which is 1 minus sine square x, that is cos square x, right? So now we have 2x minus 2. Now what we will do, we'll separate this integral into two integrals, right? See how we can do it. We can write it as 1 over cos square x minus sin x over cos square x, right? And now we can rewrite it as 2 times integral of 1 over cos square x is sec square x, and here we have sin x over cos x is tan x, and 1 over cos x is sec x, right? So now we have reduced this integral into two known integrals, because the integral of secant square x is simply tan x, and the integral of tan x sec x is equal to sec x, right? And here we have the constant of integration, which is written in the beginning, right? So now we have 2x minus 2 tan x, and then we have plus 2 secant x, right? So viewers, the integral I1 is now given by 2x minus 2 tan x plus 2 secant x. So viewers, our solution is now given by y sin x is equal to, we have this integral, that is 2x minus 2 tan x plus 2 sec x, and here we have the constant of integration, right? So this is the general solution of this differential equation. Now we have to find out the particular solution of the given differential equation by making use of these values, that is x is pi by 4 and y is equal to 0. So these boundary conditions will give us the value of this constant of integration. So when y is 0 and we have x is equal to pi over 4, here we have 2 times pi over 4, then we have minus 2 tan pi over 4 plus 2 times secant of pi over 4 and plus c, right? So we have substituted these values over here. So this term becomes 0. This is pi over 2. Tan pi by 4 is 1. So we have simply 2. And the secant pi over 4 is square root of 2. So we have 2 root 2. And here we have c. And now c can be written as taking all these quantities to the left hand side. We have 2 minus pi over 2 minus 2 root 2, right? So the constant of integration is now given by this value, right? So now substituting c over here, we get the particular solution, that is y is y sin x is equal to 2x minus 2 tan x plus 2 secant x plus 2 minus pi over 2 minus 2 root 2, right? So this is the particular solution of this differential equation.